Did you ever read that book, From the Earth to the Moon, Jules Verne? I think it's 1865. I mean, the book is so old. But so, in spoiler alert, there is a group that has a launched. It's essentially a projectile motion, and they launch it from the Earth to the Moon. And at some point in their journey, the people are in there. I'll draw a little bit bigger. They're standing like this. And then they say, oh, at some point we have to flip. We have to go through zero gravity, and then we have to flip over, and we'll have to go like this. Stand the other way. Because at some point we're going to be closer to the moon, and the moon's gravitational force will be greater than the Earth's gravitational force. And so at some point it'll be zero. And so the question is, where is that gravitational force equal to zero? So we could call this M equals 1,000 kilograms if you want, or we could just calculate the gravitational field. It doesn't really matter. But where is that? Where, the moon is a lot less massive, so it's not going to be in the middle point, right? Because the gravitational force from the Earth is greater. So let's find this out. And one of the things that's always fun to do is to draw the Earth and the moon system. I don't think this is to scale. I just did it on the paper. Everyone always draws these too close together and the moon too big, but the moon is much smaller than the Earth and pretty far away compared to the size of the Earth. So it's really hard to draw. So I know the radius of the Earth. I wrote that down. Don't even need it actually, because this is their center to center distance. The center of the Earth to the center of the moon is 3.84 times 10 to the 8th meters. The mass of the Earth is 5.972 times 10 to the 24th. The mass of the moon is 7.35 times 10 to the 22nd. And if I have an object at some location, I can calculate the gravitational force. I have two. I have this one, F, we'll call it Fe, the gravitational force due to the Earth. And then we'll have this one, Fm, the gravitational force due to the moon. And so when those two are equal, the net gravitational force will be zero. So how do we calculate gravitational force? Well, in general, Fg, let's leave it as just a scalar. That's the magnitude. Fg is going to be g, mass of the object, mass 1, m over r squared. So as I move further away, these forces are going to change. And so the question is, at what point they're the same? So let's say this is the origin and this is the x-axis. In that case, I can say their location is x. And then if this is the distance REM, then this distance is going to be REM minus x, right? Because here to here is REM, here to here is x, so that leaves the leftover distance is going to be REM minus x. So now I can write up my I'm going to set the magnitude of the gravitational force due to the Earth equal to the magnitude of the gravitational force due to the moon. So that's going to be g, mass of the Earth, the object mass, let's leave it at m, divided by x squared, right? Because in this case, the distance to that point is x, so I square that. And that's going to be equal to g, mass of the moon, mass, over REM minus x quantity squared. So I just need to solve this equation for x. So let's do that. Let's make sure we have plenty of room. So here I have g, mass of the Earth, mass over x squared equals g, mass of the moon, mass over REM minus, and that's just a constant, minus x quantity squared. So the first thing I can do is do some cancellation. I can divide both sides by g. I can divide both sides by the mass. So now I have me over x squared and m moon over this. Now I'm going to multiply both sides by x squared and multiply both sides by this. So I get REM minus x quantity squared times the mass of the Earth equals mass of the moon times x squared. I want to solve for x, right? So, but I can't get x on one side because I have this term in here. So let's do some tricks. What if I take the square root of both sides? If I do that, I get REM minus x times the square root of me equals the square root of m times x. And yeah, there is a plus or minus in there that's going to matter, but let's just not worry about that for right now. Now I can multiply this out. I get rem times the square root of me minus x times the square root of me equals the square root of times x. Now I can add this to both sides, and I get rem, the square root of me equals, and I'll write it out, x times the square root of me plus x times the square root of Now I can factor out the x. I get x times the square root of me, that's the e, plus the square root of Now you cannot just make that all one square root. That's not the same thing. So be careful about that. Now I can divide both sides by this, and I get x equals this thing, rem, square root of me over the square root of me plus the square root of Done. Okay, let's go ahead and put our numbers in. So I had, I'm going to leave off the units, 3.84 times 10 to the 8th. Then I have the square root of me, which is 7.35 times 10 to the 22. And then I have that divided by the square root of 5.972 times 10 to the 24th plus the square root of 7.35 times 10 to the 22. And I have to divide that on the bottom. Now, don't be careful. You can't cancel these. Don't do that. That's a bad idea. But you'll notice this is in units of meters, and all these have the same units, so the units cancel. I'm going to switch over to Python and calculate this because I don't like typing that in my calculator because I'm a big baby when it comes to calculators. So let's switch over to Python just as a tool to do this. I can go ahead and put in my constants here. This is a better way to do it. I don't actually need this one right now. 6.67 times 10 to the negative 11th is g. me is 5.972 times 10 to the 24th. m is 7.35 times 10 to the 22. rem is 8.84 times 10 to the 8th. Okay, so now I see the nice thing about doing it this way, I can really just type that equation. I can say x equals rem times the square root of me divided by the square root of me plus the square root of I mean, I don't have to put in the numbers. That's the whole nice thing. And if I need to change these, I can. So then I can just print that. Let's just say x equals x meters. And let's do this. Print percent distance. Yeah. So what percent of the way have you gone? So that's going to be equal to x divided by rem times 100. And then I'll put that as a percent. I think that might work. The percent thing sometimes is weird. Okay, so let's see. Earth to the moon calc. 0g. It technically is 0g. Okay. And Jules Verne actually said that would be 0g and you'd be weightless, and you wouldn't be weightless other parts. You would in fact be weightless the whole time because you're accelerating the same as the spacecraft. But 1865, someone that says that, I think that's pretty good. Okay, so 90% of the way there is when you would flip around, according to my calculation. That seems... Yeah, because the mass of the Earth is, on the order of 100 times greater. Let's just make a plot. Let's not leave this here. Let's plot the magnitude of the gravitational field, which is just going to be g m1 over r squared, as you're moving from the Earth to the Moon. Let's plot the magnitude of the Earth's gravitational field, the magnitude of the Moon's gravitational field, and the total. So I'm going to first make a graph, g1 equals g curve. G1 equals graph, and let's put the title, x title, as the x distance is going to be just r in meters. I should probably put that in r in, well, that's fine. And then the y title is going to be equal to g, the gravitational field, in newtons per kilogram. And now I'm going to get Fe is going to be g curve. Color is color dot green, I guess. Let's do blue. And then I'll do Fm is the gravitational field for the Moon. G curve color equals color. Let's just leave it as black. Black is default. And then Ft is the total. G curve color equals color dot red. So now I need to start with my x value. I'm going to start on the surface of the Earth. So actually, that's a good idea right there. So Re equals, what is it? I wrote it down. 6.37 times 10 to the 6th. That's my starting value. So I can say x, let's say r. And I'm just going to do a scalar version. So r is going to be equal to Re. Dr, what's my step size? How many pieces do I want to get to go all the way across? Let's do 1,000 calculations, right? So it's going to be Rem divided by 1,000. So that means that it's 1,000th of a step. It's an easier way to do it. I could say a meter, but who knows how long it'll take. Now I'm going to say while r is less than, I don't want to go all the way to the Moon, because then I will get an infinite amount. Actually, I think let's actually start this at 3 times the radius of the Earth. And let's go to, as long as it's less than let's just do Rem minus the radius of the Earth. I'm just making up something. Okay, so step 1, I'm going to calculate the gravitational force of the Earth, Fe, capital. It's going to be G times Me divided by r squared. F moon is going to be G times mm divided by, now I have to take the Rem minus r squared, right? Because that's the distance. And then I can find the total, Ft. It's going to be equal to, let's call the Earth is to the left, so it's going to be Fm minus Fe. So we're dealing with scalar versions here. I made it in the x direction. Now I can plot this stuff. Fe dot plot r Fe. Fm dot plot r Fm. Ft dot plot r Ft. Now I have to move my r value. So r equals r plus dr. And let's run this and see if I don't break something. So the red one is the total. Okay, so I think that's okay. The red one's the total in the negative direction. So when I'm over here, it's mostly dominated by the Earth, right? It goes up to a very high value. And I have over here, it finally ends up going greater than the Moon. But I can't see what's really going on over here. So let's go from right here. That's an x value of 1.58 times 10 to the 8th. So I'm just going to change this and say r equals 1.58 times 10 to the 8th. And let's just rerun it. So I'm starting over here. I'm starting a better part of the way. There, and now we can see, here's where does the total is the red one. Right there. Right there is where it crosses from being closer to the, or more gravitational from the Earth to more gravitational to the moon. That's where, in Jules Verne's world, it would be weightless. Okay. So I think that graph's pretty fun to see. It's good practice plotting, graphing, and seeing how things change. That gives us the power of doing 1,000 calculations to see how this works. So that's just a physics problem for you. All right, I'm going to end it right there.